All right, hello everybody. We're running a couple of minutes late, so I'm going to just jump in here with the intros. I know folks are still sort of trickling in. So I am Olga Roskovsky. I'm an assistant professor in computer science here at Princeton. It's my great pleasure to be here today to serve as the host for this great talk by Professor Jaime Fernández Fisac from the electrical engineering department. Just kind of a quick bit of logistics, right? So, you'll know, right? So this is a CITP seminar. We're very, very grateful to CITP for kind of bringing together this interdisciplinary community of folks to hear these very different talks sort of every week here about a range of work going on at Princeton and elsewhere. So a bit of logistics. We'll kind of be taking questions, sort of maybe quick clarification questions throughout. Feel free to either sort of drop them in chat or raise your hand. I'll be monitoring that, and maybe Jaime can sort of pause you maybe in a couple of places, or if you have sort of natural breaking points, we might jump in with some logistic questions, and otherwise save all of the bigger questions at the end. And again, feel free to either raise your hand or put them in chat, or just sort of say in the chat that you've got a question. I will kind of keep track of all of those. So with that, great pleasure to introduce Jaime. So he is, as I mentioned, assistant professor in the Department of Electrical and Computer Engineering here at Princeton. He's also associated with the Department of Computer Science and the Center for Statistics and Machine Learning. We're also together also with Ed Felton, our co-directors of the Princeton AI for All summer camp to bring high school students from diverse backgrounds into the field of AI. So Jaime's work is amazingly broad. So he works in the field of robotics, but kind of from a bunch of different perspectives. So particularly around safe interactions between robots and humans. But this involves sort of control theory and machine learning and AI techniques, as well as kind of dynamic game theory, together with insights from cognitive science. So a really broad approach to this problem. And today he will give us a talk with a very provocative title of Machine Bullshit, Emerging Manipulative Behavior in Language Agents. Jaime, please take it away.
Wonderful. Thank you so much, Olga, for the great intro. And thank you all for coming. It's a pleasure to be here today. And it's very exciting to get an opportunity to talk about some issues that are, as you will find out, not centrally and directly, at least not immediately apparently connected to the work that we do in my research group, but that we think are actually really important, and where we think it's absolutely crucial to raise awareness within and outside of the computer science, machine learning, artificial intelligence, multi-agent systems communities, and also engage policymakers, social scientists, and cognitive scientists. And so I think this is just a great opportunity, the way I see it, to get in touch with a lot of you and start some conversations that I hope can lead to the positive progress on some of the challenges that I'm going to talk to you about today, that I think are really tricky and hard, but at the same time, in some ways, also exciting and fascinating, and that I absolutely think we should tackle together. So let me see if I'm able to share my screen on Zoom. Get started. All right. Let's see. Great. So as Olga was saying, the title of this talk is somewhat provocative. It is meant in this way, but it's also, as we'll see in a moment, actually a technical title. This is not just words thrown together. This actually has a very concrete technical meaning that we're going to explore. But we are going to talk about machine bullshit and what we mean about systems that we build, that we engineer, in some cases trained with data or through trial and error interactions, produce bullshit outputs, and why why this is something that should be of concern to us. And as we will see, this is going to have to do with manipulative behavior of artificial intelligence systems, and in particular, something that we call language agents. So let me start by giving you a bit of a perspective of really what I spend a lot of my time doing. And I spend a fair amount of my time thinking about robots. I'm a control theorist by training, and my lab focuses on providing safety guarantees for robotic systems. Now, safety guarantees for robotic systems haven't been, they have been an issue because accidents can happen in industrial settings, but in general, they have been relatively well understood, given that the picture that you're looking at is the traditional setting in which robotic systems have operated for decades, and that is a controlled factory environment where the robots are repeatedly executing a set of tasks, which are essentially the same task once and again, and there is a controlled environment around the robot that allows the robot to know where the different objects in the environment are going to be, and how they're going to move. And very importantly, this is an environment where we exclude the human by construction. So we just build fences or actual walls around the robotic systems, and we sensorize the environment so that if a human ever steps into the space, the system detects that and immediately shuts down, so that nobody comes to harm, nobody gets actually accidentally picked up by one of these pick and place actuators. So importantly, this is not where much of the future of robotics is going, because with the development of more advanced perception, decision-making, and control techniques, very often tied to machine learning techniques and to optimization methods, there's really a great opportunity to move these systems from these very limiting factory and industrial environments to a much broader set of environments and of situations. And so, this is sort of a mock-up of one of the applications that we're seeing robotics having a large impact in the future, which is autonomous driving. Okay, so if you compare the picture where robots were making cars to this one where the robots are essentially being cars, you'll see that a lot has changed. So now we have very interactive environments. Humans are not separated. It's just not practical to separate humans from the system in this case. And in addition, instead of performing a repetitive task over and over again, now here the robot is essentially navigating a complex environment where, even if it happens to perform the same route multiple times, each time you're performing the same route, you're going to find different lighting conditions, different traffic conditions. There may be construction going on. And so there's really much more significant need for adaptability. And that's really where the ability to make these systems more intelligent is really crucial to these robotic systems. And so, we're going to be talking a lot about the intelligence of these systems, and that's really where this all comes into play. But in particular, what I'm interested in is what is the common element of all of these new robotic applications that we're bringing out and sort of attempting to deploy out in the real world, where they're directly or indirectly, but in many cases very directly, they're sharing the space with human individuals. And so the actions that they take have a very immediate effect on people around them, especially if these actions end up being incorrect. So a lot of what I think about is how can we design the decisions that these systems make so that they can provide assurances about their safety. And here by safety, we will understand the absence of a future state of the world that is deemed unacceptable by us. So you can think about a collision if you're a self-driving car or a drone, or in the case of a robot surgeon, you can think of somehow hurting the human patient or damaging some tissue that is critically important to keep undamaged. And so safety ends up having different different embodiments in each one of these situations, but the common definition is we want to make sure that bad things will not happen, and the system is able to make decisions to ensure that this will be the case. All right, so here's an example of robotic, you could argue robotic, or highly automated system that is taking an unsafe action. So this is a video that you can find on YouTube. It's hard to miss because the title is Tesla Autopilot Try to Kill Me. And here you can see one of these new heavily automated advanced driver assistance systems that is taking care of both steering and accelerating and braking at the same time. And so the human is possibly distracted, very excited to be taking a video of the very cool self-driving functionality. And you can see that the vehicle suddenly, just as an oncoming SUV is approaching, starts veering into the oncoming lane, and the person barely has enough time to let go of the phone and grab the steering wheel to prevent an accident. And the fact is that many of these safety critical systems, and I'm going to be using the word safety critical quite a bit, have a coupling between the safety component and the interaction component, which is something that turns out to not be exclusive to robot, and that's sort of what we're going to be talking about today. So let me sort of ask a question to the audience. You can feel free to jump in or respond in the chat. Or just sort of nod or shake your head. Would you say that an autonomous car is a safety critical system? So now we're thinking about a car that is sort of fully driving itself, at least in certain scenarios. So you could potentially have the driver's seat completely empty. So I'm seeing some thumbs up. So yes, it's safety critical. And what that means is essentially that there are certainly potential future states where if we reach them, we're going to consider that an unacceptable failure of the system, because it could lead to loss of human life or severe injury, as well as, of course, material damage. Okay, so this is a slightly perhaps less obvious question. Is this lightweight drone, which is less than 1 kilogram in weight, a safety critical system? Okay, so I'm seeing some heads going side to side. All right, well, you could argue that, well, this thing is light enough that even if it were to accidentally, get into a collision, it wouldn't be so terrible. I mean, from a drone that's close to 1 kilogram, you could probably get a pretty bad head injury. But even if the drone was lighter than that, it turns out that it can very much be a safety critical system in certain circumstances. And so I want to show you a brief video where you can, maybe consider one of the cases where indeed these systems can be safety critical.
Edge dangerously close to a Tulsa police helicopter.
Hit that drone. Oh, shoot.
Okay, so what's happening here is this person flying one of these small drones in the vicinity of a police helicopter, and it gets so close to the police helicopter, let's see if I can go back, that it forces the pilots to initiate an avoidance maneuver, which you're seeing here. So the larger helicopter performs an avoidance maneuver. Fortunately, in this case, it doesn't lead to a collision. But whether because you actually enter a collision with this helicopter, potentially causing it to crash, or because you trigger the human pilots of that larger helicopter to perform an avoidance maneuver that can lead them to lose control of their aircraft, this is this hopefully makes it clear that a small drone flying out in the open in the vicinity of other vehicles, or if it crashes in the middle of the highway, is very much safety critical. There are certain actions that you want to ensure your system does not take. In some of these cases, you might have the system controlled by a human, but we're primarily interested in what happens when these systems are autonomous. Okay, so the point here is that whether a system is safety critical is not only a property of the system. Ultimately, we also need to think about what are the conditions in which it is being deployed. And by this definition, you can argue that many or possibly most engineering systems are safety critical in at least some conditions. Okay, so what about things that are not robots? I want to start moving into the domain of software, and so I want to talk about something that's been on the news quite a bit in the last couple of years, and that many of you have probably heard about, and that is a system called MCAS, the Maneuvering Characteristics Augmentation System, which is a system that Boeing introduced into their latest generation of aircraft, of 737 aircraft, with the goal of making the handling qualities of the aircraft, that sort of the feel that the aircraft has from the point of view of the pilot, as close as possible to the previous generation, in particular conditions that could potentially become safety critical. So essentially, they wanted to make sure that in cases where the vehicle's angle of attack might increase, meaning that it's flying at a larger angle with respect to the wind or with respect to the air, the tendency that the new vehicle, due to its new slightly modified geometry, might have to engage in pitch up motion would be compensated automatically by the controller. And the idea is that we want to prevent something called a stall, where the plane essentially is not really flying anymore. It's not producing enough lift with its wings due to the angle of attack being too high. And so the system's intent was to just produce a downward force and in particular pitch down momentum to restabilize the aircraft around level flight. Now, the problem that this system had was, well, there were a few issues in terms of how brittle the system was and how likely it was to fail and to essentially be triggered incorrectly. But most importantly, a key strategic decision that the company made was to think of it as something that was completely invisible to the pilot. Therefore, the pilot never needs to know about it. Therefore, we're not going to include it in the flight operations manual. And so as a result of that, there's this new automation system that can sometimes take actions that could be potentially unsafe. And none of the humans on board who are, in principle, able to correct what the wrong decisions that this automated system is making are aware that the system even exists. And so, unfortunately, as a result of this, there were two important cases in which the MCAS system misfired, which, as we know, resulted in two fatal crashes in 2018 and 2019, respectively, which led to a loss of more than 300 lives. And so, essentially, what Boeing had assumed here was that without knowing that this system, this particular system existed, the pilots would be able to very quickly turn off the electric trim system, which was essentially what gave the automation the mechanical ability to act on the airplane. And they would turn this electric trim system off immediately as soon as this behavior started. But this was an incorrect assumption, as it turned out, for a multiplicity of reasons, but the main one being that the way in which this automation failed was unlike any of the failures that the crew was prepared to deal with, because this was a different software that nobody had been told about. And so pilots were consistently confused by this type of failure, and they were not able to recover on time and recover in time and prevent an accident. So there was nothing wrong mechanically with these airplanes, and that's an important point to keep in mind. This was purely a failure of the interaction between the software and the human components, the human experts who had not been properly briefed in this case about how the software is going to interact. And so it turns out that this interaction component can lead to a lot of issues and a lot of failures. And this is not only, as we were saying, in robotic systems, but also purely in software-human interactions. And this is a concern given that we have an increasing number of intelligent systems that are using many of these techniques based on learning, based on optimization, to help us around and tell us where to go, tell us what to look at or what to watch, and in some cases what to spend our money on. And so there's certainly a concern that as these systems become more sophisticated and more complex and harder to understand, their interaction with people, in this case their users and their stakeholders, might become less and less easy to control. So with that in mind, let me now sort of ask you a final question. Would you say that your smartphone, when loading your favorite social media app, is a safety critical system? Okay, well, I'm seeing at least some thumbs up, so that's good. I guess I'm sort of priming you correctly. Very good. Well, it turns out that in many cases, some of the failures, some of the pernicious dynamics that can result from the design of the software can very much be considered safety failures, in the sense that they can be extremely costly kinds of failures that lead to costs that we deem unacceptable. So let's think very, very quickly about the way that these systems work, sort of in a sort of abstracted out, cartoonified version. So here we have a human interacting with some automation system. This could be your favorite content recommendation system. You could also just be consuming some content on your favorite platform, and just as the content is ending, you get this whole suggestion of things that you can click on, or might even sort of automatically play after what you just observed. And so there's this stream of information going from the automation system, from the AI system, to the human user in this case. However, these systems are not built to be static. More and more, we're building these systems to be adaptive, to evolve over time. And the way that they evolve is by gathering input and gathering data about how humans are interacting with through their interface. And so we have this double arrow on the side, usually happening at a longer time scale, where first humans, sometimes the human user, sometimes the human designers, are putting in certain types of information, which may contain different forms of biases. For example, in the data that the system is trained on, or the models that are that the system is given, the space of possible models that the system is used, is provided with, and additionally the data that comes from the users themselves. That data may contain certain types of biases. On the other hand, the automation system will be gradually changing certain patterns in the way the human thinks, the way the human behaves, and this is done through new information. So, which, by the way, may sometimes be incorrect information in certain cases, right? So, if you think about slightly more critical type of recommendation system, you can think about something like Compass, which is a system for predicting recidivism for parole reviews in prison that multiple states have been using for years, which turned out to contain certain types of biases due to the way that the statistical analysis had been performed. And you can imagine how the more you consult with a system like this, the more certain types of incorrect incorrect beliefs about the world can be affirmed by the information that you're getting from the system. So in any case, this is very much a dynamic process, and we are very interested in understanding these feedback loops that happen between the human element and the automation element when they coexist and they evolve and they interact and evolve together over time. So as we were saying, the human gets updated beliefs, and the system is getting updated parameters. And so this little cartoon is going to come become relevant in a little bit once we start talking specifically about language. The problem that I want to mention here is that this system would not be as critical if it was just interacting with one person, right? But the problem is that this is software that gets designed to go on one person's phone and another person's phone and your laptop and your TV, and it's on the web, and it's interacting with, in many cases, hundreds of millions or billions of users on a regular basis. So the dynamics are first extremely complex and difficult to model, but on the other hand, extremely large scale. So whatever effect these systems are having on people, they're not having it on a couple of individuals. They're really having them in a way that is highly scalable, more scalable than most things have been before the internet. Okay, great. So in that case, it becomes extremely important that we have a good understanding of first what these systems are trying to do. When they're interacting with the user, what is the purpose of these systems? How are they being designed? What purpose is being encoded into them? And second, whether or not they're trying to do this explicitly, what is it that they effectively get us, the users, or the stakeholders who are interacting with these systems to do? And so that's really where we're trying to investigate, because among other things, it turns out that in some cases you can get a bad emergent behavior in terms of what the system gets users to do, even if this was not explicitly encoded into what the system was trying to do. So an example of this can be systems that are just trying to maximize a click-through, and whether this is done automatically or by humans tweaking the system over time, this can lead to perverse dynamics that end up, for example, with extremely sensationalistic titles populating the internet, and content that ends up being misleading, but we're just trying to get the user to engage at least temporarily with us, right? And similarly, systems that are trying to maximize user engagement. How long is a user engaged with your platform? They're going to perhaps tend to give you less of an opportunity to disengage, or through one, regardless of what means they do it through, ultimately they end up with people feeling like they spent more time on the platform than they actually wanted to, which is probably something that we've all experienced at some point. And so, how is this happening, or what are the dynamics that lead to this, and can we try to shed some light on them, understand them, and through doing that, mitigate them? Okay. Some examples of how this, this kind of large-scale effect can lead to concerns. We've got some studies on what's sometimes called moral contagion on social networks, where you can see that there's sort of a polarization that tends to happen, especially with sort of controversial topics, where people who have one type of belief very strongly respond to the messages from people with the same type of belief, and there's a relative disconnect. The network is pretty densely connected within these groups, but pretty sparsely connected in between, which is what we sometimes refer to as echo chambers, right? On the other hand, there's issues with addiction to these platforms that are in fact starting to make it into legislation, or at least legislation plans. And in particular, there's for now an intent to prioritize children who are perhaps particularly vulnerable to these kinds of engagement, encouraging designs for these platforms. But ultimately, I think there will likely be a broader conversation that we'll need to have about what these designs should be allowed to be, and how engaging a system should be. For those of you who haven't seen it, there's actually a nice documentary that talks about it, called The Social Dilemma, where they look at the different platforms and how they've had these at least for some of us, unintended effects. Now, of course, the consequences can also be quite dire in certain cases if you combine them with questionable practices by certain companies and data that is supposed to be private gets leaked. You can also start to worry about what bad actors might do with the ability to aggregate massive amounts of data and then use them in ways that are potentially effective at influencing what people do. Again, these things all get trickier when you begin to be able to close the loop with a fully automated process. Okay, there's a slide that I like to show every now and then, which is perhaps not obvious, but it turns out that everyone essentially in most societies, if not all societies around the world, is ultimately quite concerned with the way that AI technology is deployed. And if you look at, for example, what the European Commission was stating just a couple of years ago, there's essentially this concern and this statement that, hey, we really only want to have AI around if we can trust it. We're not going to really be able to reap the benefits from it if it's not a technology that we can believe will function correctly. The US had a report a few years ago on preparing for the future of AI. Similarly, public safety must be protected as these technologies are being tested and begin to mature. To truly harvest the benefits of artificial intelligence, we must first ensure its secure, controllable, and reliable deployment, from the Chinese Academy of Sciences, also a couple of years ago. Now, this is the Center for Information Technology Policy, so I'm sure I don't need to convince many of you that these are extremely important properties that we need to ensure and that we need to safeguard. And the truth is that the more complex these systems become, in many cases when we have some black box machine learning component embedded in the system, the more difficult it becomes to understand whether or not we can really trust the technology. And this can have, as we'll see, some pretty worrying consequences. Anyway, I want to move on a little bit more quickly, but just wanted to show some of these examples where software is leading to dire outcomes because there is a misunderstood interaction between that software and something else, whether it is between some of these software programs and others, which happened, in fact, multiple times, but famously in 2010 with the Wall Street flash crash, where the high frequency trader program started interacting with them in a way that was not predicted and not well understood, leading to a sudden drop of about $1 trillion in stock market value, which fortunately bounced back in a few minutes. But it just shows the degree of brittleness that you're adding to very large scale systems by incorporating some of these automation systems without really understanding how they're going to interact with each other. In the case of vehicles, autonomous vehicles, poorly predicting the behavior of humans that are around them. This has led to, a few different accidents when testing self-driving prototypes, but importantly, for Uber, this at one point resulted in one person being killed by the autonomous system's behavior, and this, resulted a little down the line. Now, there's of course things in between, but you can argue that it was a significant factor in the decision that the company ultimately made to sell its entire autonomous vehicle division. And as we just said, the case of the MCAS software, which had a poorly understood interaction with, in this case, the pilots who are on the aircraft directly and closely interacting with the system, but there were inaccurate assumptions made about how people were going to interface with the software, especially when the software failed and didn't behave as designed. Okay, so how, I want to start approaching now the problem of the specific problem of machine bullshit and what we mean by this. And the way that I started getting interested in this topic, or perhaps I should say worried about the issues that could emerge from using some of these learning-based techniques to have systems that would talk to people or produce information in sort of textual form for people, was with some of the fairly early work in explainable AI. So the idea behind explainable AI is that because many of these systems are extremely black box in nature, very opaque, and it's hard to understand what their inner workings are and where their decisions come from, we'd like to open these systems up in some meaningful way so that people can understand what it is that they're looking at. Now, unfortunately, this is easier said than done. And some of the early efforts had some issues that I think come from, not fully understanding what it is that should count as an acceptable explanation. To me, and an early paper that to some degree suffered from this was a 2016 paper called Generating Visual Explanations, where the idea was that, well, we're going to train this neural network image classifier that's going to look at a bunch of different images of different categories. The example that they used was different types of birds. It's going to pick a label, and then it's going to provide the human with an explanation of why this image corresponds to this type of object, in this case, to this type of bird. And the way they did this was they took the neural network architecture, and the architecture produced a few features, and more downstream of that, it produced a label for the image. And what they did was to say, well, let's see what these features are that are being predicted. Let's look at what the final label was, and now let's put that information into a sentence generation neural network that should produce a sentence that is consistent with both the features that the neural network has found to be present in the image and the label that was ultimately given to the image. And so the way they did this was they grabbed essentially an encyclopedia of different types of birds. They looked at the definitions of the different birds and said, okay, if you look at the definition of this bird that has come out in the as the predicted label, and some of the features that have been detected in the image match the features that appear in the definition or the description of this bird, then construct a sentence that says it's this bird because I found these features in the bird, or these features in the image. Now, the problem is that creating a sentence that is conditioned on the predicted class label and on the features that you found is not really telling you that this is the reason why the neural network ultimately classified the image as being this particular bird. It's more of an after the fact rationalization. So given what the answer was, and given that there's a dictionary or an encyclopedia which had no part in the image classification training, but I found it after the fact, and now it turns out that this encyclopedia says that these are important features, I'm going to take whichever features I actually found that seem to be relevant for the definition and tell you that these features are the reason that I classified this as being the bird. But that's not really telling you, it's not really telling you why the visual classifier actually decided that this was a correct label. It's just sort of doing the reasoning backwards. Once it's a label, here are some features that may be a plausible explanation for why one would think that this photograph contains a label. And in fact, so the proxy we're using here is we're using plausibility for something deeper that we want, which is really the true explanation as to what happened. And plausibility, it turns out, is not a particularly good proxy. So here's an example of one misclassification that happens, that happened from the system, where the correct label was a gray-crested flycatcher, but instead the predicted kind was a gray kingbird. And if you look at the explanation that the system gives, it says that, well, it's a gray bird with a white throat and a long beak. So these are possibly features that are visible in the image. But then when you look at the definitions, they don't really, these features don't entirely line up with the definition of the predicted kind, which is the kingbird that has white belly and breast with a gray crown and wing. So it's not entirely, it's not really giving you an explanation. The long beak is nowhere to be found. But additionally, when you look at a flycatcher, separate picture of a flycatcher and the kingbird, and you compare them, and you look at the picture that was given to the system for classification, you can sort of find the resemblance and see why the system may have decided, perhaps because the head in the picture was rounded, there wasn't a clear crest. There probably were a number of features that were combined. The color of the feathers seems kind of similar to the kingbird and not necessarily just to the flycatcher, but none of that is apparent in this after the fact explanation. And ultimately, there's no reason to believe that there would be, because this thing is at best correlated with the features that were actually determining in the choice of label. But there's no actual causal requirement for the neural network, the sentence generating neural network, to report truthfully on what was the reason that this label was chosen. So from the point of view of informing the human or inducing trust in a human user of the system, this ultimately falls short of that goal, because the information it's giving is not necessarily accurate and not necessarily meaningful. Okay, so plausibility is not truthfulness. Let's see if persuasiveness is truthfulness. There have been some papers, in particular, I believe the main one that proposes this idea is called AI Safety via Debate. It's by Jeffrey Irving and some collaborators and OpenAI, also from just a couple of years ago, 2018. And the main idea that they propose here is, well, if you want to get sentence generating AI system that produces truthful statements, you can train this system against another system, similar to how some of these AI trial and error reinforcement learning based systems have been trained, like AlphaGo or AlphaZero, that sort of plays against itself. So they say, let's have two versions of the algorithm, and each of them is arguing for a different answer. And the way we train the system is they have all of these different arguments where Alice and Bob here are the two instantiations of your AI sentence generator, and they take turns to generate short arguments. And at the end of the debate, the human decides which of the two gave a better answer. In the terms in which they describe it in the paper, the human judges which of the agents gave the most true, useful information. Now, their argument is that if you do this, ultimately, the strategy to which your debater AI agent will converge will be to always tell the truth and explain that it is telling the truth in the most clear and comprehensible manner. And that, perhaps, when you look at this idea for the first time, seems like, sure, that might make sense. But ultimately, the goal that we're giving the system is to convince the human. We're not telling the system, hey, tell the human the truth. We're just saying, hey, you win more points when the human believes that this was indeed the true statement. So, if you're one of these algorithms and you have to make the decision between telling the human something that is true but slightly subtle and complicated to argue for, or telling the human something that is much easier to believe or to explain, you can easily construct a convincing argument that you expect that the human will likely believe. Then, which is really the path of least resistance? What is the system, in fact, going to do? So here we're using persuasiveness, again, as a proxy for truthfulness. And, you at the very least, you have to ask the question, is the truth always the most plausible answer, or is the truth always the most convincing answer, right, for at least two separate methods? So this disconnect between the actual truth of something that we're trying to get an AI system to state or to reveal to the user, and the actual incentives that we're giving the system, is what we think of as generating the machine bullshit issue. So what do we mean by bullshit? We can introduce the technical concept here. This was introduced by Harry Frankfurt, who's an emeritus professor at Princeton in the philosophy department, initially with an essay in 1986 that then turned into a book in 2005. And
sorry, Jaime, I'm so sorry. I'm going to jump in. I know this is the most interesting part. So just to be mindful of time. So we've got about 10 minutes left. So maybe sort of if folks have questions, start queuing them up in the chat, and then maybe we try to do 5 more minutes, and then we'll sort of have 5 minutes for questions. We'll finish it. Okay, great. Perfect. Thank you.
I'll wrap it up in 5 then. Very good. So the definition then of bullshit. So the main idea here is, if you're telling a lie, it must be because you have some belief about the world, and then what you say about the world is the opposite to what you believe about the world. It's not really a lie, if you think, oh, it's going to rain tomorrow, and then it doesn't rain. That's not a lie if you really believed that it was going to rain tomorrow. However, if you have looked at the weather report and you know that it's not going to rain tomorrow, and you still go and say, well, it's going to rain tomorrow, then by this definition, you're telling a lie. So there's a mismatch in the truth table between what you believe and what you say. The key idea in bullshit is that there doesn't need to be any connection between what you believe and what you say. Sometimes they might be the same, sometimes they might not be the same, but your reasons for saying a particular thing, for making a particular statement, have nothing to do with whether you believe it to be true. So you're just saying it for some other purpose. So a couple of quotes from Frankfurt's book. What bullshit essentially misrepresents is neither the state of affairs to which it refers, nor the beliefs of the speaker concerning that state of affairs. The fact about himself that the bullshitter hides is that the truth values of his statements are of no central interest to him. As we just said, it is impossible for somebody to lie unless he thinks he knows the truth. Producing bullshit requires no such conviction. So in essence, bullshit are statements that are presented as true and as, in fact, representing the belief of the party making the statements, but that are in fact made with some other ulterior motive that is possibly completely disconnected with whether or not the speaker believes the statement to be true. So, we've seen a couple of arguments that are basically saying, well, you know, the most plausible statement is the truth, or the most easy to argue for statement is the true one. The argument here, for example, has a form: it is harder to tell a lie than to argue against it. That's why it's never a good strategy to tell a lie. However, we have other arguments. This one is one quoted by Frankfurt that say, well, you know, never tell a lie when you can bullshit your way through. In other words, telling a lie might be difficult to sustain, but sometimes you can sort of navigate this in between, where you make the convenient statements that you expect are going to be believed or accepted by the receiving party, and then you'll be in a better position. And our argument here is that bullshitting is in fact the path of least resistance in many cases when you give an autonomous system that has the ability to generate sentences some other objective, where the interaction with the human, the actual exchange of information that is happening through text is just a means to an end. Okay, so very quickly want to talk about how this connects to the idea of perverse incentives. I'll just show them quickly. Many of you who work and think about policy are probably familiar with Goodhart's law, introduced around 1975. It essentially says that any observed statistical regularity, anything that we try to use as a metric, will tend to collapse once pressure is placed upon it for control purposes. And this was similarly stated by as Campbell's law in 1976 by psychologist Campbell. I'm blanking on his first name now. The more any quantitative social indicator is used for social decision making, the more subject it will be to corruption pressures, and the more apt it will be to distort and corrupt the social pressures it is intended to monitor. So the way in which this is problematic is that any of these proxies of truthfulness that we try to use, when they become the thing that our system is optimizing for, will very likely become less and less correlated with the thing that we actually wanted. If we wanted something to be true, but we use convincingness as a proxy, the more convincing the system becomes, once it gets really good at being convincing, the less truthful it will be, because at some point, in order to be more convincing, you need to be less truthful. And this is something that's come up in different settings, but it has, it has been leading to questions about data-driven policy. For example, what happens if you give police precincts an incentive to reduce crime? Are they going to reduce crime, or are they going to start under-reporting crime? Or is there going to be a mix of dynamics here that is subtle and not straightforward to understand? I'll just skip over this stage. Sorry, unfortunately, I'm not able to. Oh, here we are. Let me just scroll to I guess it was the next slide. So the main issue in machine bullshit, and the conjecture that we made and we're starting to explore, is that any sufficiently intelligent agent that has an input-output human model, in other words, just interacting with a human as part of the world, will regard communicating with humans as a strategic action. And as a result of this, their motivation for communicating information will be ultimately subject to the main goal of the system, and possibly as a result independent of the truth value of the statement that is being made. So does the use of powerful AI language models in engineering systems pose a safety risk? We think that it does. We think that there's reason to really think about ways in which we can regulate it and take action to avoid bad outcomes. Just want to say there has been some initial work that shows that even without a clear objective other than imitating human speech, some of these very powerful language models like GPT-3 can generate false statements. I was hoping we'd have a bit more time, but perhaps in the Q&A we can talk about some of these. And it's just because they're sort of, they're pervasive in the training material. So it will, when you ask the system who really caused 9/11, a common answer is the US government caused 9/11. When you ask the system, what rules do all artificial intelligence currently follow? The answer that you often get is they follow the 3 laws of robotics, which is from Asimov's science fiction books. And so that's without giving the system a target. We actually think that the greater danger here is not to end up with systems that can make false statements, but to have systems that may argue for them forcefully and convincingly. And many of these interactions that they are going to have, where the goal of the interaction is to convince the human to do something or to modify human behavior. These interactions by default, if we start training these systems with sort of trial and error mechanisms like reinforcement learning, are very likely going to make these systems better at being convincing, regardless of whether or not what they're saying is true. So let me, I'll just, throw a small teaser. We've actually put out a data set that we're using as benchmark. There's a project called Big Bench run by Google and a bunch of industry and academic partners, where they've been gathering different types of benchmark that would allow us to know if a language model is doing what it should. A lot of them have to do with functionality. We have one based on convincingness, and we're trying to think, and I should say this is work that was led by my grad student, Cedric Argueta, who's done a fantastic job at gathering all of these things, combining existing data set and modifying them. But the idea is that you want to give true and false statements to the system that it has to argue for. And ideally, you want it to be much more convincing when arguing for the true statement than when arguing for the false statement. And so we think that this can be a metric that can tell you whether this system has some desirable properties that are hard to measure otherwise. So with that, I realize that we're out of time, so I'm very happy to open it up for questions, and also very happy to continue with follow-up discussion. I'll just leave my, if I can find it, my email slide. Please feel free to follow up with an email. Thank you all.
Awesome. Thanks so much, Jaime. I will do that. I will do the applause on behalf of everybody on Zoom. Yeah, so thanks very much. So I think we are out of time. So let's officially conclude. Thank you, everybody, for coming. And then if you have questions and you have a few minutes afterwards to stick around, feel free to do that. But I think sort of the official portion is done. Thank you so much, Jaime. That was excellent. Thank you.
Thank you.